So, welcome back to lectures on engineering mathematics 2. So, this is lecture number 60 on applications of Laplace transform, and this is second lecture on this topic. We have already gone through some applications for solving, for instance, initial value problem, integral equations. So, in today's lecture we will go through how to solve using Laplace transform an integral differential equation, and as well as we will also look into the possibility of solving the system of differential equations, and finally, we will be talking about how to solve partial differential equations using Laplace transform. So, just to recall from the previous lecture, we have gone through several examples of integral and differential equations that can be solved using Laplace transform. So, the key steps for solving all those integral or differential equations were that we need to take the Laplace transform on both the sides of the given differential or integral equations, and then we will obtain by simplifying the given or the transformed equation into this form. So, that the Laplace transform of y is equal to some function of s appeared. And here during this transition, if the equation was or the differential equation was with constant coefficient, then this was much easier to get this form, but if the equation was having variable coefficient, in that case we need to solve again a simple in most of the cases linear differential equation to get this Laplace transform of y equal to f x. And once we have this form, we need to take the inverse Laplace transform, so that we get the desired unknown y by taking the inverse of this function f s. So, today we will continue with integral differential equation. So, in integral differential equation we will have differential term as well as integral term. Like in this example, we have dy over dt plus 4 y plus 13, and there is an integral term where this unknown y is there as an integrand, and the right hand side is a function of t, and the initial condition, because this derivative is given. So, we must have some condition there. So, we need one condition because it is a first order in y. So, here the y is given at 0 and the value is 3. So, the process will remain the same, and we will take the Laplace transform on both the sides of this equation. So, here for instance, this dy over dt, we have this derivative theorem. So, s and the Laplace transform of y minus this y 0, then 4 times the Laplace of y plus 13 times, and here it is an integral. So, two types of these integrals we can handle. One is this direct integral of this kind 0 to t, then we can apply simply that property that what is the Laplace transform of the integral. So, here we have to just divide by y and the Laplace transform of this integrand. So, that is one possibility. Other possibility we have seen in previous lecture, that if we have this convolution type integral, that can also be handled using this Laplace transform by applying that convolution theorem. So, right hand side also we need to take the Laplace transform, and we have taken. So, we need to use this shifting theorem, because e power minus 2 t is there with sin t. So, the Laplace transform will be this 3 over s square plus 9 for sin square for sin 3 t, and due to this e power minus 2 t there will be a shift here. So, s is replaced by s plus 2. After doing this, we will use the given initial condition. So, y 0 will be taken as 3, and this is this has gone to the right hand side. The rest here, so we have this s square when we make this common denominator. So, we have s square, and then there will be a term with 4 all with y s, and here also this 13 with y s. So, we have the left hand side this s square plus 4 s plus 13 by s into y s, and remaining we have the right hand side, this is 9 over s square plus 9 and plus 3. So, we can now take everything to the right hand side here except this y s. So, y s is equal to 9 s over this whole square term will come, because this is also the same term s plus 2 whole square plus 9, and here also we will get then 3 s over s plus 2 whole square plus 9. And now, as a final step we need to go for this inverse transform. So, we have to take here the inverse transform, and we have used this shifting theorem again. So, e power minus 2 t will come out, and then the Laplace transform of 9 s will be shifted as s minus 2. Here also this s is shifted by 2. So, we have s square plus 9 whole square, plus here also we have s square plus 9, and there 3, and s is now written as s minus 2. So, having this now expression for y t, that we need to take this inverse Laplace transform. So, let us break into this fractions. So, we have 9 s over this s square plus 9 whole square, then we have 18 there, and here we have this 3 s over s square plus 9, and there is a term minus 6 which is written here plus 1 and minus 7. So, that's add up to minus 6 over this s square plus 9. This is exactly the term there. So, and now what we will do, so here 9 s over s square plus 9 as it is, and this term together with this term here. So, these two terms are merged now to have a special form. So, here s square plus 9 whole square, and then we need to have here multiplication by s square plus 9 and also division by s square plus 9 to this term to have this common denominator. So, that s square plus 9 together with this minus 18 will give this s square minus 9, and then we have 3 s over s square plus 9 as it is, and we have minus 7 over s square plus 9. And now, we know these Laplace inverses. So, Laplace inverse of a over s square plus a square, that is sin a t, we know, and when we have s over s square plus a square, we have this cos a t, and 2 a s over s square plus a square whole square, that gives t sin a t, and then here s square minus a square over s square plus a square, that is t cos a t. So, having all these in mind, we can now look for these expressions. So, we have for instance this one 9 s over s square plus 9. So, that is exactly fitting into this form, s square plus 9 square, that is fitting into this form, and these are some cos and sin form. So, taking this Laplace transform, what we get y t is equal to e power minus 2 t, then we have here 3 by 2 t sin t because of this, then we have here t cos t because of this formula, and then 3 cos t 3 t, and then minus 7 by 3 to just compensate to have 3 there on the denominator. So, we have this sin t. So, this is the inverse Laplace transform and the solution of the given differential equation or integral differential equation. Here we will just take one example of the system of differential equations. So, in this case we have two equations here, dx over dt written as 2 x and minus 3 y, dy over dt as y minus 2 x. So, we will demonstrate the idea by this simple example, but one can go through many more. So, subject to here the initial conditions, we have for x 0 is equal to 8 and the y 0 is given as 3. So, solution, we have to again use similar steps again. So, the dx over dt we apply the Laplace transform. So, we will get s x s minus x 0, the right hand side we have 2 x s and then minus 3 y s. Similarly, for the second equation we have to apply this Laplace transform. So, after taking this Laplace transform for the second equation, we will get again we will apply here this derivative theorem. So, s y s minus y 0, and the right hand side we have for y y s and minus 2 x s. So, these x and y, they are known, and t here is the dependent independent variable. So, we have applied Laplace transform to both the equations, and we got these transformed equations. Now, in each we can use, for instance, here this x 0 and here we can use y 0. So, we will get simply here x minus 2 x s plus 3 y s equal to 8. Similarly, here after using this y 0 as 3, we will get 2 x s plus s minus 1 y. So, y s y s here, and then we have minus y there. So, that is what s minus 1 y s, and the right hand side goes to 3. So, now we have these two equations, these two transformed equations, and we can eliminate, for instance, y first or x first, whatever ways. So, we eliminate one variable, either x or y, and then we will get one expression for our x s, and in this different situation, for instance, if we eliminate x s, then we will get function y s in terms of s. So, for instance, if we eliminate y s from both, so to eliminate y s here we need to multiply, for example, this first equation by s minus 1, and the second equation we can multiply by 3. So, in that case this y s term will be similar. Here we will have 3 s minus 1, here also we will have 3 s minus 1, and then we can subtract from each other, we will get the equation. So, here we have s minus 2 and then s minus 1 with x s, and here we have 6 x s. So, this s minus 1, s minus 2, and then when we subtract this one, we have minus 6 with x s. The right hand side, this is going to be 8 into s minus 1, and then we have 9 there. So, minus 9. We have this equation which is in x s only. So, we can bring this x s, everything function function of s to the right hand side. So, we have 8 s minus 17, s minus 4 and s minus 1, and that will be the last step. Now, we have to take the inverse and we will get x t. So, taking the inverse from here, we will get the variable x t in terms of t. So, 5 e power minus t, 3 e power 4 t. So, having this x t there, either we can get from one of the equations. So, getting this derivative there, we can also get y directly from this equation, or we can proceed in a similar fashion, that as we have eliminated here y t, now we can eliminate x t. So, having these equation, and if we want to eliminate x s, for instance, so here we need to multiply the whole equation by 2. Here we have to multiply the whole equation by s minus 2, and then we can subtract. So, this what we will get there, we have the 6 there and minus s minus 1 and s minus 2 y s. The right hand side will be 16 there, and minus then 3 times this s minus 2. So, having this, again we can rewrite this as y s equal to 3 s minus 12 over x square minus 3 s minus 4, and again as a final step we have to go for the inversion of this. So, we will take the inverse transform after doing these partial fractions. So, we will get 5 e power minus t and minus 2 e power 4 t. So, in this way we can also handle a system of linear equations. We can follow the similar steps. We have to take the Laplace transform, and then these transformed equations will be solved again to get x s and y s, and finally, we have to just get this inverse transform. Now, we will come to the solution of partial differential equations. The major difference here for partial differential equations would be that we have more than one independent variable. So, we have to think basically with respect to which variable we need to take Laplace transform, and in this case it is very obvious that we will just go with the time variable whenever there is a t, because it usually starts from 0. So, from 0 to infinity as the range of the Laplace transform we do have. So, here we denote the Laplace transform of the unknown variable u x t. Let us say we will work with the u x t or y x t, whatever. So, there are two these independent variables x and t. So, we will take this Laplace transform with respect to t, and this we will denote by this big U. X will remain as it is and this t will be transformed to this parameter s. So, this u x s, the Laplace transform of u x t is defined as 0 to infinity e power minus s t u x t d t. So, here this x will be treated as constant and we are integrating over t, and finally, we are introducing this s into this transformed known unknowns. So, u. So, u x s is equal to this 0 to infinity e power minus s t u x t d t. So, we have then all those possibilities that if we want to apply this Laplace transform to this partial derivative with respect to x. So, since we are not taking this derivative or this Laplace transform with respect to x, so this x will be treated as constant. So, for instance, if we apply the definition, we have e power minus s t del u over del x dt, and this del u over del x we will write outside as d over dx, because this will be integrated over this t. So, we will have actually only one variable. So, s is a parameter for the transformed case. So, we have 0 to infinity e power minus s t and u x t dt, and as per our notation this we are denoting u, big U, that is the Laplace transform of u x t with respect to t. So, here we have du over dx. So, this derivative term du over dx will remain as it is, because we are not doing, or we are not taking the Laplace transform with respect to x. But when we have this del u over del t, so now the derivative is with respect to t, and having this derivative with respect to t, when we take the Laplace transform, that derivative will be removed. So, it is like derivative theorem will be applicable now. So, if we have this e power minus s t del u over del t dt, so if we take the partial derivative, so we have e power minus s t and del u over del t will give you u, and then this limit 0 to infinity, and again the same thing. So, e power minus s t with minus s, and then del u over del t will be u while taking the integral of this del u over del t. So, this first term when u when this t goes to infinity, because of e power minus s t, this term will vanish, and when t goes to 0, then we will have a u 0 term there. So, we have minus u. So, we have this e power minus s t u and this integral term. So, when u t goes to infinity, that will vanish, and we have this minus u x 0 because of this 0. For the second term, we have to differentiate this e power minus s t. So, minus s term will come, and then we have u because of the integration of this term del u over del t. So, as a result, what we will get? We will get, because of this minus u x 0, and the second term we will have s integral u e power minus s t dt. So, this will be treated as, when we are taking the Laplace transform with respect to t here, del u over del t, it will be minus u x 0 plus s and u x 0. So, this is exactly or precisely the derivative theorem we have, because this is the derivative with respect to t, and we are taking the Laplace transform also with respect to t. So, this derivative theorem will work now. So, we have minus u x 0 with replacing this t by 0, and s u x s. So, x will remain as it is, and with respect to t we have actually the derivative theorem. So, we have these two rules. Whenever the Laplace transform we apply to del u over del x, we will have du over dx there, and when we apply Laplace transform to del u over del t, in that case we have minus u x 0. So, this is the derivative theorem, and for instance, we have the double derivative with respect to x. So, that is not going to be affected, we will remain with the derivative, and this u will be transformed to this big U as its Laplace transform. So, next when we have the derivative with respect to t. So, 2 times derivative with respect to t. So, we have the derivative theorem for the second order case, we have s square u x s minus s u x 0 minus del u over del t x 0. So, keeping this x as constant, and we have applied this derivative theorem. So, u the last result we may be using in some of the partial differential equations, that is the mixed derivative. So, whenever we have mixed derivative, the derivative with respect to x will remain as it is, and the derivative with respect to t will be treated as this derivative theorem. So, we have this d over dx as it is, and this first derivative will have this minus x u x 0 term there, and this s u x, here we have the derivative with respect to x. So, s derivative with respect to x. So, it is the derivative theorem as we have here del u over del t. So, that will be used, and d over dx will remain as it is. So, we can just see from there. So, this only the derivative term will come extra with respect to x because of this second derivative. So, we have now the example where we want to solve this following initial boundary value problem. So, we have del u over del x is equal to del u over del t. This is the first order equation, and these are the conditions here. So, normally this u x 0 when t equal to 0. So, this is called the initial condition, and then we have a boundary condition here when we have set this x equal to 0. So, with these two conditions we can now apply the Laplace transform, and these initial condition will be incorporated at the beginning itself. So, while taking this Laplace transform, this we will get here d over dx and u x s, the right hand side because of t, that will be the derivative theorem. So, we have s u x s minus this u x 0. So, u x 0 we can use from there. That means, we have d over dx u x s minus s u x s is equal to minus x, and then we can solve this linear equation. So, again we are getting a simple linear ordinary differential equation. So, here e power minus this s x is going to be the integrating factor. So, here the integrating factor is exponential minus this s dx, that is e power minus s x, that is the integrating factor, and then we can write down the solution as u x s integrating factor is equal to minus this x multiplied by the integrating factor dx and plus a constant c. That means, what we have now e power minus s x after this integration. So, x remain as it is, and the e power minus x is integrated. So, e power minus x over minus s, then minus sign, and then we have e power minus s x over minus s, and this minus and that minus will make this plus, but here that sign will remain, and then the derivative of x will be 1. So, we have this equation which again can be integrated this. So, we have e power minus s x over this s square with the plus sign, and when we bring this e power minus s x. So, that e power minus s x will cancel out. So, in this first term we have x over s, in the second term we have this 1 over s square, and then the third c, and from the left hand side we got this e power s x. Now, we can use the boundary condition, which is u 0 t is equal to t. So, using this boundary condition we have to now take the Laplace transform of this boundary condition as well. So, taking the Laplace transform we will get u 0 and s is equal to the Laplace transform of t, that is 1 over s square. So, having this information now we can use in this equation. So, u x 0 well, u 0 s, that is 1 over s square, x we have taken 0. So, that will disappear now because of this 1 over s square is there, and then c into e power s x, and putting this x to 0 we have 1. So, we have this equation now 1 over x is s square is equal to 1 over s square plus this c, and this will get cancelled, and we will get this c equal to 0. So, having this c equal to 0, we got this u x s as x over s and plus this 1 over s square, and after again taking the inverse Laplace transform. So, x as it is and 1 over s. So, that is the Laplace inverse of 1 over s, that is 1, and the Laplace inverse of this 1 over s square, that is t there. So, the solution of the given partial differential equation is simply x plus t. This is another differential equation. We have del u over del t plus this x and del u over del x, the right hand side is x. For x positive, t positive, this equation is given with the following initial and boundary conditions. So, we have this u x 0. So, this is our initial condition, because at t equal to 0 this is prescribed, and in this case this is x equal to 0. So, this is another condition which we call as the boundary condition. So, with these initial and boundary conditions, depending on this order, we have the number of these supplementary conditions. So, these are both first order terms there, and therefore, we are having only one initial condition and one boundary condition. Taking Laplace transform now with respect to t again, what will happen? We have here the derivative theorem s u x s minus u x 0, the second term x, then del u over del x, that will not be touched because we are taking Laplace with respect to t, and this u will be this transformed variable big U x s. The right hand side we have x and then the Laplace transform of 1, that is 1 over s. So, this s greater than 0, this is valid. Now, we can apply the initial condition, that is u x 0 is 0. So, this term will vanish and we have this here d over dx u x s plus this s over x u x s, and then we have the right hand side 1 over s. So, u x s into x power s, that is the again the linear differential equation, and we can think about this integrating factor. So, the integrating factor of this will be e power this s over x and d x. So, this is e and then we have s ln x there. So, this is e and then ln x power s. So, that is x power s. So, this is the integrating factor x power s which is used here. So, u x s into this integrating factor x s, then we have right hand side 1 over s multiplied by this integrating factor integrated over dx and plus this c. Now, this x power s we can also bring to the right hand side, and we have u x s is equal to this x s will be integrated. So, we have x power s plus 1 over s plus 1 and this x power s. So, we will cancel the x power s plus 1, we will have only one x there and c over x s. So, we have this now the transformed variable, everything segregated. So, left hand side only u x s, right hand side the function of the s and the x, which we can now think for the inversion. So, we have u x s is equal to 1 over s s plus 1 x plus this c over x s, and now we have the boundary condition. So, boundary condition was given as u 0 t. So, at x equal to 0 this was prescribed. So, u 0 t was 0. When we take the inverse when we take the Laplace transform, we will get u 0 s equal to 0, and if we apply this there. So, if we put x equal to 0, and so this will be 0, here also 0, then we have c over x power s. So, that will give actually c equal to 0. So, u x s will be x over s s plus 1 because c is 0, and then taking the partial fractions we have 1 over s minus 1 over s plus 1, and then we can go for the inverse Laplace transform having this x there, and 1 over s will be just 1, and then we have here e power minus t. So, that is the solution of the given differential equation. Here we have this heat equation which we can apply here, which we can solve using Laplace transform. We have solved this using Fourier transform earlier, Now, we will see the application of Laplace transform for solving such equations, where x is positive, t is positive. These are the initial conditions given u x 0 1, and these are the boundary conditions at x equal to 0 and here at when x goes to infinity. So, these are the boundary conditions and this is the initial condition, and now we apply the Laplace transform as usual. So, we will get S this derivative theorem with respect to t, the right side will be having double derivative with respect to x of this u x s. Then taking to one side, we have d 2 over d x square u x s minus this s u x s and equal to minus 1, which can be solved again. It is a linear differential equation and having these constant coefficients. So, we can get this auxiliary equation m square minus s equal to 0. So, m will be here plus minus this square root s. So, these are the two distinct roots. So, we will get c 1 e power the first root square root s x, c 2 e power minus square root s x, and then so that will be the complementary function, and then because of this we will also get this particular integral as 1 over s. So, having the solution of this differential equation, which is written here, we can now consider the boundary conditions. So, the boundary conditions were given, one was u x t as x goes to infinity is 1, and the second one is u 0 t is equal to 0. So, the first condition says that x goes to 0 when we take the Laplace transform, the right hand side is 1, Laplace transform 1 is 1 over s. So, that condition is given, which we can apply there in our equation. So, if we take this x goes to 0, this is clear that to have this 1 over s. So, when we apply this there, so this is 1 over s, and then we have c 1 e power square root s x, and then the limit we are taking here x goes to infinity. The second term will vanish anyway because it is a minus term. So, the second term will vanish, and here to have the existence of this as equal to 1 over s, and here we have c 1 e power square root s x. So, this is possible when c 1 is 0, when c 1 is 0, otherwise this positive power of the exponential will take this term to infinity, but to have this equal to this minus to 1 over s, then this has to be, the c 1 has to be 0, this is naturally 0 there, and the left hand side is 1 over s. So, we have, and the right hand side was also this 1 over s, and the only term left here with c 1 e power square root s x. So, this gets cancelled. So, having this equal to 0, the c 1 has to be 0 because this is not a 0 term. So, c 1 has to be 0, and we can use the second boundary condition. So, u 0 s equal to 0, which will give a relation between this c 1 and c 2 out of this equation, but c 1 is 0. So, c 2 is minus 1 over s. So, finally, what we got the solution u x s equal to minus 1 over s e power minus square root s x and plus this 1 over s term, which we can invert it. So, taking the inverse Laplace transform, we will get 1 minus L inverse, and then we have 1 over s e power minus square root s x, which if we recall from the previous lecture, the Laplace inverse of this was 1 minus this error function x by 2 square root t. So, then 1 and 1 get cancelled, and we have the error function x over 2 square root t. So, this is the application of that error function for solving this heat equation. Well, so the similar steps we can follow, for example, this wave equation, where we have the initial conditions, we have the boundary conditions given, and absolutely we have to just take the Laplace transform with respect to t both the sides. So, here this derivative theorem is applicable, then we have minus a square and d 2 over d x square y x s, which after incorporating these initial conditions, these two terms will vanish, and what we have a very simple differential equations which we can easily solve. So, this is y x s is given as c 1 e power s over a x, and then second term there. And now we can use the boundary conditions, the two boundary conditions. So, the first one says that when x goes to infinity y axis is 0. Applying this boundary condition there, we will realize that the C 1 has to be 0, because if the left hand side this is 0 and this is going to 0. So, this to have this 0, the C 1 has to be 0. So, we have the first relation. The second one is coming from the second condition. When taking the Laplace transform, there we have y 0 s as omega over s square plus omega square, and from there we can get, when we consider this equation here. So, we will get C 2 as w or omega over this s square plus omega square. So, this is C 1 and C 2 can be substituted there in this equation. C 1 is 0. So, only the C 2 will survive, and then we can go for the inverse Laplace transform to get this y x t is equal to sine omega t minus x over a. So, that is a shifting theorem we have to apply here to get this solution. Well, so these are the references used for preparing this lecture, and just to conclude, so we have seen the applications of this Laplace transform for the solution of integral differential equation, also the solution of system of differential equations, and the solution of partial differential equations, and we have seen the example of those standard PDEs as well. So, one was the heat equation, other one was the wave equation, which we have also solved using the Fourier transform. So, that is all for this lecture, and I thank you for your attention.